We begin day 2 of the linear programming unit. First off, last class period, I had you pick 10 ordered pairs that worked and 10 ordered pairs that did not work in our cookie problem. Here you will see many of the points that worked in green on the left and those that didn't work on the right. Now, separately, they don't look like much, but when you put them together, they look like something like this. Okay, there is a definite boundary, for lack of better words, between what works and what doesn't. So today what we're going to do is we're going to start looking at those constraints or rules and figuring out the boundaries. Now, the way in which we're going to do this is, since they have maximum values, we're going to use inequalities, because inequalities will allow us to use those values or values smaller than that as well. In order to do this, the best way to do so is to have a few examples. So in the next 3 slides, you will find 3 different examples that you will need to fill in your notes as we go through them. The first example states, in an archery competition, a shooter scores 5 points for each arrow hitting the center and 3 points for every other hit. Assuming that she at least hits the target somewhere with every arrow, how many arrows will it take to score at least 37 points? So to do this, what we have to do is first decide what our variables are. Well, in this problem, they're talking about hitting a target, and we have 2 different types of shots. You can either hit the target or you can hit the target in the center. So that is going to be our 2 variables. So you don't have to use x and y, but I'm going to go ahead and use x and y because that is what you're used to. We're going to let x equal if the person hits the target, and we're going to let y equal if it hits the center. So that way we know the difference between the 2. Now, for every time the person hits the target, they get 3 points. So say if we don't even ever hit the middle, we get 3, then 6, then 9, then 12. And each time what we're doing is we're adding 3 on, but even more importantly, we're taking the number of times they've hit the target times the amount of points. To write this as an equation, or a term, would be 3x. Now we can do the exact same thing, but this time we'll do with hitting the center. Well, they get 5 points as the rate as every time they hit the center. So we say 5y. Now they want to score at least 37 points. So my total has to be at least 37. And normally when you calculate points, you add together values. Now here's the catch. They want at least 37, which means we want 37 or 38 or 39. So what we're going to have to say is 3x plus 5y has to be greater than or equal to 37, because we want more points than that. Now all we have to do is properly label our graph and graph our scenario so we can find a variety of points that would work in this scenario. So I'm going to label. So the x-axis is hitting the graph, and the y-axis is hitting the center. Okay, before I go to label my x and y by however many points, first I probably want to find my x and y intercept. Now, I know we've used 2 methods for graphing. One is rewriting it, and then the other one is using intercepts. And I would like for you to practice using intercepts. So what we do is we create a t-table having x and y, and I'm going to let x be 0. Now, in that inequality, if x be 0, then we get 5y is greater than or equal to, but I'm going to just imagine it's equal to 37. Now, to solve this math problem for y, we divide 5 on both sides, and we get 37 divided by 5, which is 7.4. Now I'm going to repeat this process, but I'm going to let y be 0. Well, 5 times 0 is 0, so I'm left with 33x equals 37. If I take 37 divided by 3, I get 12.3 repeating, which is 12 and 1/3, but I'm going to just put 12.3 repeating. Now, if you look at your graph, as high as you're going to have to go is 12. So we probably could go by 1, so we won't have to label a bunch of stuff. I'm going to probably go out every 5 and label. So 5, 10, 15. And when you do these, you want to try to make the graph as big as possible. So if you have the choice between going by 1s or by 2s, go by 1s. You want the graph really big. Okay, I'm going to do the same on the other axis. So I'm going to go up 5, 1, 2, 3, 4, 5, label it 5. Okay, go up 5 more. 1, 2, 3, 4, 5, label it. Then I'm going to plot my points. Grab a different color. So my first point is 0, 7.4, and that's my y-intercept, so I approximate where that is. 12.3. 12, so 12.3. Now this is greater than or equal to, so it will be solid. Please make sure that you are using a ruler for this because precision is the key when we're doing these math problems. So I'm going to connect those two. Now theoretically, this line would go on forever, but we have to remember there's actually a couple constraints or rules we're not thinking about. Okay, we can't have a negative number of hits. We can't have either case, hits or center. So that is why we're only using the first quadrant. Now all I have left to do is pick an ordered pair and test it. I'm going to pick 0, 0 because it's down and to the left. Even though it is the origin, it will work. So it's 3 times 0 plus 5 times 0 greater than or equal to 37. Well, 3 times 0 is 0, 5 times 0 is 0. Add those together, we get 0. That is not greater than 37. So 0, 0 is not true. Now, if you notice 0, 0 is down the left, so we're not going to shade that region. We're going to shade up and to the right. So my feasible region is everything above that line. So what this is telling me is if my person gets any ordered pair number shots, whether it hits the center or hits the, just hits the target in general, I'll have at least 37 points. Okay, let's try another one. Example 2. A farmer needs to plant his fields in the next 3 days. It takes a half an hour to plant each acre of wheat and 3/4 of an hour to plant each acre of corn. If our farmer plans to work 12 hours each day, how many acres of each should he plant? So we have two variables here. We're talking about wheat and corn. And for the sake of doing something different, I'm going to say let W equal the acres of wheat. And let C be the acres of corn. It says a farmer needs to plant the fields in 3 days. Now, if you look, 3 days actually has 2 rules because 3 days, he's working 12 hours each day. So if we're working 3 days for 12 hours, the most hours that this farmer will do is 36. Now, he will not exceed the 36 hours because it says if our farmer works this much. So rather than this constraint being a greater than or equal to, it's going to be a less than or equal to. Now, my 36 is in hours, so we can change everything so that it's in hours as well, and they are already. It says a half an hour per acre of wheat. So just like before, we're going to say half, but I'm going to use decimal. Half an hour per acre of wheat. Now, here's why using W and C helps a little bit, because I can tell which one's which without having to look back up to see what X and Y represent. 3/4 of an hour is 0.75 for corn. And normally when you do time, you don't subtract time, you add your times together. Okay, so now I'm going to label. If you look, I listed wheat first, so I'm going to put wheat on the x-axis. Wheat in acres. Off the side, I'm going to do corn. And of course, that is as well in acres. So before I can label anything on my graph, I need to figure out what my intercepts are. Wheat, corn. If I let wheat be 0, it's kind of like I have 75 hundredths of corn equals 36. So what I need to do is divide both sides by 0.75. If I take 36 divided by 0.75, I get 48. Now I'm going to repeat the process, but I'm going to let corn be 0, which means I'm going to have half of wheat is equal to 36. If I take 36 divided by a half, or by 0.5, I get 72. Now this one, we probably won't be able to go by ones. It will not fit. So we have an option. We could go by 5s. We could go by 10s. Well, let's just kind of skip every other and see what we have to start with. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. So if I go by 2s, I wouldn't have enough. I could possibly go by 5s. That make 5, 10, 15, 20, 25, 30, 35, 40, 45. Nope, not big enough. So I'm going to have to go by 10s. So each tally is going to represent 10. So I'm going to label every other one. 20, 40, 60, 80. I'm going to repeat the same process up the side, counting every 4, and that's going to represent 20. Now, if I would have done every box was 10, my graph would be so small that later on, when I go to calculate things, I will not be able to read my graph, and that is very important. Okay, I'm going to plot my values. 0, 48. Well, halfway between 40 and 60 is 50, so I'm going to go just slightly there below. 72, 70, 72 is just going to be slightly to the right. I look, and once again, it is less than or equal to, but it's not greater than or equal to. So I'm going to draw my line in, and it's going to be solid. I'm going to pick an ordered pair to shade. I'm going to pick 0, 0, because it's down and to the left, is 0.5 times 0 plus 0.75 times 0 less than 36, which it is. So I'm going to shade down and to the left. Now be careful, you're not using negatives because we can't have a negative number of acres. That is why our wheat and our corn must be at least as large as 0. There is my feasible region for that constraint. Let's try one more. Let me grab a pen. Last question's about tomatoes. You plant tomatoes in the spring so you can have you can make salsa in the fall. One variety grows large tomatoes and the other one grows small tomatoes. So those must be two of my variables, large and small. Now you can use whatever you want. I'm going to use L, but I'm going to use a cursive L because my ones look like L's. So L is going to equal large tomatoes, and S is going to equal small tomatoes. It says you expect about 15 large tomatoes per plant and 25 small tomatoes per plant. So this is kind of working the same way as our last one, 15 per large, so that'd be 15L. 25 per small, so 25S. How how many plants of each type should you plant to get at least 180 tomatoes? So we want 180. We want at least, so we want either 180 or more than that. So we're going to say greater than or equal to. Now, just like before, we're not subtracting, we're adding because we want to add up all our tomatoes because we're putting them all in our salsa. Okay, so I have my large. Now, don't forget, if you do yours in reverse and you have your smalls on your X and your large on your Y, that's fine. Just make sure you label it so I can see what it is. Because what will happen is your graph would be a reflection of mine. Okay, so now I'm going to make my table. I have large and small. I'm going to let large be 0. That means 25S has to equal 180. So I take 180 and divide it by 25. And that's 7.2. Now I know you can't have 2/10 of a tomato, but think of it, it could be a rotten one. Okay, so now I'm going to let my small plants be 0. Well, that's going to leave me with 15 times the number large has to equal 180. So I take 180 divided by 15, and I get 12. Now, those aren't big numbers, so I should be able to go by ones. So I'm going to count out, going by ones. I'm going to label every 5th one. So now all I have left to do is plot those points, draw my line, and shade. So 0, 7.2, 12, 0. Now, do you understand 12, 0 means that I would have to have 12 large plants and no small plants, or I'd have to have 7.2 small plants and no large plants. Now, once again, it is solid because it says equal to, so I'm going to draw my equal to. I'm going to pick my point. I'm going to pick 0, 0 again. Okay, I'm going to test 0, 0 is 15 times 0 plus 25 times 0 greater than 180. It is not. So I'm not going to shade 0, 0. I'm going to shade the opposite. This here is my feasible region. If I pick any ordered pair on that line or segment or in the shaded region, it should work in my math problem. So I hope this has been helpful. This is graphing and writing single constraints. So after you get done with this, you are to do the worksheet that I have provided for the sub along with graphing each of the constraints. Make sure your graphs are precise, you've used a ruler, and everything looks good in them.